Welcome to the study of statics. Statics is the branch of engineering mechanics that deals with bodies at rest or in equilibrium. In statics, we analyze forces acting on objects to ensure they remain stationary. Forces are interactions between objects that can cause them to accelerate. In statics, we balance these forces to prevent motion. Vectors are mathematical tools that represent forces. Unlike simple numbers, vectors have both magnitude, how strong the force is, and direction, which way it acts. Vectors are crucial in statics because they allow engineers to combine forces mathematically and predict whether structures will remain stable or fail. This analysis prevents dangerous collapses and ensures the safety of buildings and bridges. Vectors can be broken down into their horizontal and vertical components using trigonometry. This is essential for analyzing forces in engineering problems. Consider a force vector F acting at an angle theta to the horizontal. We can resolve this into horizontal and vertical components. Using trigonometry, the horizontal component is F times cosine of theta, and the vertical component is F times sine of theta. For example, a 4 Newton force at 30 degrees has horizontal component 3.46 newtons and vertical component 2 newtons. Understanding vector components is crucial because it allows us to perform calculations on multiple forces acting on a single object by breaking each force into its x and y parts. The graphical method of vector addition, also known as the head-to-tail method, involves drawing vectors to scale and placing them end to end. Start by drawing the first vector from the origin to its specified magnitude and direction. Here, vector A is 5 newtons at 30 degrees. Next, place the tail of the second vector at the head of the first vector. Vector B is 7 newtons at 45 degrees. The resultant vector is drawn from the tail of the first vector to the head of the last vector, showing the combined effect. The length of the resultant vector represents the magnitude of the combined force, while its direction represents the direction of the combined force. This method is particularly useful for visualizing how multiple forces combine in simple systems. The component method provides an analytical way to add vectors, which is more accurate than the graphical method. We resolve each vector into its x and y components using trigonometry. For vector A, the x component is a times cosine of its angle, and the y component is a times sine of its angle. Similarly for vector B. To find the resultant, sum all the x components to get rx, and sum all the y components to get ry. The magnitude of the resultant vector is found using the Pythagorean theorem, square root of rx squared plus ry squared. The direction is found using arctangent of ry over rx. Equilibrium occurs when the net force acting on an object is 0. This is expressed mathematically as sigma F equals 0, where sigma represents the sum of all forces. For a particle in equilibrium, this means the vector sum of all forces acting on it must be 0. No acceleration occurs when forces balance perfectly. This equilibrium condition applies to each coordinate direction. The sum of forces in the x direction must be 0, and the sum of forces in the y direction must also be 0. Free body diagrams are essential tools for solving equilibrium problems. They show all forces acting on a particle as vectors, helping us identify and sum the forces. To draw a free body diagram, represent the particle as a point and show all forces as arrows emanating from that point. Each arrow represents a force vector with magnitude and direction. To solve equilibrium problems, we begin by drawing a free body diagram that shows all forces acting on the object. Consider a 200 N weight suspended by 2 identical cables at the same angle. The free body diagram isolates the weight and shows the forces, the 200 N gravitational force downward and the tension forces T1 and T2 in the cables. Choose a consistent coordinate system with x horizontal and y vertical. This helps organize the force components. Resolve each tension force into x and y components. Both tensions have the same angle θ, so T1 has components T1 cos θ left and T1 sin θ up, while T2 has T2 cos θ right and T2 sin θ up. Apply the equilibrium equations. For Ceph x equals 0, the x components of T1 and T2 must balance, giving T1 cos plus T2 cos θ equals 0. For Ceph y equals 0, the y components plus the weight must balance, giving T1 sin θ plus T2 sin minus 200 equals 0. Solving these equations simultaneously, since the cables are identical, T1 equals T2. Substituting gives 2t cos that equals 0 and 2t sin that equals 200, so each tension is 100 N. A moment, also called torque, is the tendency of a force to cause rotation about a point. It's calculated as the product of the force and the perpendicular distance from the point to the line of action of the force. The sign convention for moments follows the right-hand rule. Counterclockwise rotation is considered positive, while clockwise rotation is negative. Moments are essential in statics for analyzing the equilibrium of rigid bodies, ensuring that both translational and rotational equilibrium are maintained. Structural engineering brings together forces, vectors, and equilibrium principles to create safe, stable structures that surround us every day. Consider bridge design. A bridge beam experiences downward forces from its own weight and traffic. Support reactions push upward to maintain equilibrium and prevent collapse. In building design, structures must withstand distributed loads such as wind, snow, or gravity. Engineers calculate support reactions to ensure the building remains in equilibrium and stable. These principles extend to all structures, from skyscrapers to dams, ensuring safety and preventing failure. Statics forms the essential foundation for more advanced engineering courses like mechanics of materials and structural analysis.